The definite integral as the area of a region. If f is continuous and non-negative on the closed interval ab, then the area of the region bounded by the graph of f, the x-axis, and the vertical line from x equals a and x equals b is given by the definite integral. We can still think of it when the value is negative, when the integral is negative, we can still think of it as area, but we don't usually think of negative area. Let's take a look, though, at a problem where we'll have some positive and some negative. All right, so here, once we combine these, it's no longer the area. So if we just look at the negative, we have the part that's below the x-axis, we have a negative area. If we just look at the part that's above the x-axis, we have a positive area. But notice that the negative and positive will cancel each other out. Some of them will cancel each other out, so it's not true area. Right? It's sort of the, we got some canceling going on here. Right? So when we're below the x-axis, we don't usually think of it as area anymore. So here we can divide these two. This is the graph, by the way, of f of x equals 2x. Right? So this is the equation that is graphed. Right? And this is going from, right, so we're finding the integral from negative 2, right? Yes, from negative 2 to positive 1. And anyway, 2x dx. So one way we could find that area is when we graph it, we see we have two triangles. We have one triangle from 0 to 1, and we have another triangle from 0 to negative 2 to 0. Okay? So the part that's from 0 to 1, we have a base on that triangle of 1. Right? The height of the triangle is 2. Right? And to find the area, we take 1/2 base times height. So we have 1/2 times 2 times 1. The area is a positive 1. If we find the area of under the curve from negative 2 to 0, right, we have a base of 2. Oops, well, that base wants to be stuck up there, I guess. Base of 2 from 0 to negative 2, and a height of negative 4 from 0 to negative 4. Right? And the area of that would be a negative 4, right? Because we have 1/2 times 2 times negative 4 equals negative 4. And if we add those together, we have negative 3. So notice that area above the x-axis is positive, area below the x-axis is negative. So we can't really think of that as being a true area, right? Because we can't, the positive area and some of the negative area cancels each other out. If we want to see it as a true area, right, as a true area, that would be 5, then we would want to take the absolute value. If we're looking for accumulations, though, we have a negative accumulation and a positive accumulation, and so together it would be a negative accumulation of negative 3. All right, so let's do one more in this video with the limit of the Riemann sums, and then we're going to look at some other ways to calculate it and kind of bring that all together in this lesson on the definite integral. All right, so first of all, let's find the change in x. All right, so that would be 5 minus 1 divided by n. That would be 4 over n, right? Because we're looking at an infinite number of rectangles. All right, so now let's get our x value. All right, so the x value is the starting value, which is 1, plus our first rectangle, which will be 4 over n, our change in x, times j. We're going to substitute into the function and simplify. Right, and so that would be 3 times 1 plus 4 over nj squared. So right, these are the x's, right? So this is we'll substitute the x into the function. Plus 1 plus 4 over nj plus 1, right? That 1 at the end, right? So all I did was I substituted into the function. So now let's simplify. So we have 3 times, all right, so this is 1 plus 4 over nj times 1 plus 4 over nj. If it helps, you can write it separately. Right? 1 times 1 is 1, and actually I could put it over here. I'll just put it like really small. 1 plus 4 over nj times 1 plus 4 over nj. All right, we would have 4nj times 1, but we'd have 2 of them, right? So 4 over n plus 4 over n is 8 over n, right? Because we add coefficients. Right? When we add like terms raised to a power. Right? And then we would have 4nj times 4nj. That would be 16n squared j squared. Plus we have a 1 and a 4 over nj and another 1. And then we could add, oops, don't forget, we had to distribute the 3, right, to the 1 plus 4 over nj. So let's make sure we don't forget to put the end parentheses there. Before we go combining any terms, let's distribute the 3 there. So we have 3 plus 24 over nj plus 48 n squared j squared. Now I can drop the parentheses. Plus 1 plus 4 over nj plus 1. All right, we can combine the things over nj. And we can combine the constants, the 3, the 1, that's 5. 24 over nj plus 4 over nj is 28 over nj. We're just adding fractions. And then we have plus 48 over n squared j squared. All right, so now we have simplified. All right, so now let's find the right Riemann sum. As n goes to infinity. Won't be long before I need to go up to the other side there, right? So we have sigma. And in front, we need the change in x, so that's 4 over n sigma. J equals 1. We're starting with the first rectangle because this is a right Riemann sum. And we stop at n, which is infinity. And then we have 5 plus 28 over nj plus 48 over n squared j squared. Right? And now we're going to split that. I think I should come over here now. We're going to split the Riemann sum. Right? And so that would be 4 over, everyone gets their own sigma. 4 over n sigma j equals 1 n 5 plus, hopefully I'm going to have enough space here. 4 over n, if not, I'll just kind of move everybody over a little bit. Sigma n j equals 1, 28 nj, 28 over n times j, and then plus, yep, everybody needs to move over just a little bit. Otherwise, this one's going to go off the screen. Sigma j equal, oops, did we, yep, almost forgot his little 4 over n there. So plus 4 over n times sigma j equals 1 to n, and that would be 48 n squared j squared. All right, so now we're going to factor out the coefficients. Nothing to do with the first term. 4n sigma j equals 1 to n 5. No coefficients there. We can factor out the 28 and the n. That's the coefficient on j. So 4 times 28 is going to be 112 n squared sigma j equals 1 to n j plus, and then we've got 48 times 4. That's going to be 692 n cubed sigma, and then we have j equals 1 to n, and then j squared. At this point, we switch to the power sum rules for sigma. And those j's now are going to become n's when we switch over to the power sum rule. There will be no sigmas. Right? So this will be, the first one will be 4n times 5n, and then plus 112 n squared, and then the j is going to be n squared over 2 plus n over 2 plus, hope you don't mind, I have nowhere to go. I'm going to have to discontinue the line because j squared needs a little bit more space than that little bit I've got there, right? 192 over n cubed, and then the one for j squared would be j cubed over 3. They match. Oh, excuse me. No j's. No j's. N cubed over 3 plus n squared over 2, and then lowly old n over 3 times 2, 6. Right? And you have these in your notes. All right, so now we're going to simplify that. So the n's will cancel. This will be a 20. The n squareds will cancel. So I'm on the next one now. N squareds will cancel. 112 divided by 2 is 56. And then one n will cancel, and the 2 and the 112 will cancel. That would be a 56 over n. The n cubes will cancel. 192 divided by 3 is going to be 64. Right? And then n squared over 2 times 192 over n cubed times n squared over 2. The n squared will cancel, and a 2 will cancel, but that's it. So let me see if I can just move this over just a little bit. I think I can get all 3, 4, 6 terms in here. We only got 2 more left. All right, so we would have a 96. That's going to really matter much because it's got an n in the denominator. And then we'll have an n squared in the denominator. And 192 divided by 6 would be 332. So all I'm doing is I'm just distributing, right? And then up here I did that. So that's how I got all my numbers there. But I just reduced. I didn't write down. I wrote down the reduced number. All right, so now we take the limit. And one little thing, I just want to, sometimes I forget to write it down once I go to the Riemann sum. And back here, we should have made it clear what we were doing. Don't be sloppy on notation. Don't do it, Mrs. Mashagna. Sometimes she forgets to write her little notation down there. All right, and then one more time. I don't need to write it where I'm simplifying for the power sum rules, right? Because we're just simplifying there, right? We're taking our values and simplifying. But once I come back to find the limit, then what we're really finding is we're finding the area under curve from a right Riemann sum, where we have an infinite number of rectangles. All right? So that we're going to have the limit of, it'll be 20 plus 56 plus 56 over n. Oh, why don't I combine them together? Hang on. I wanted to make sure I put in the fact that we were doing a right Riemann sum. And then I have like terms that could be added together instead of writing them all individually, right? So that would be 120, 140 plus 56 over n plus, oh, why don't we combine those two? So that would be over n plus 30. Of course, that's just going to be 140, right? Because the other two are zeros, right? So a little review here with the, and so even though it looks like, oh, it's a lot of work, when you think about it and just do it step by step, none of the steps were difficult, right? So that's what makes, and they're very, very repetitive, right? So that's what makes this not too hard. And really how you get good at it, you just do it, right? And it helps to have the notes out when you do it, right? So that you can remind yourself of all the steps. And at this point, you can do the one homework, that's the definite integral, and it has you using the limit of Riemann sums. Right? And I will put that into the folder so you know, hey, this is the homework Ms. Michelle is talking about. On the next video, we're going to tie all of this together and we're going to learn another way to be able to calculate out the area, the definite integral, the area under the curve of the definite integral, because we don't always have some nice power sum rules to help us out. And so it'd be helpful to have